So I hope over the past few videos I've given you a sense of just how difficult Turing machines are to work with. There are, for instance, Turing machines that don't halt and can't be proved to not halt in ZFC set theory. And the argument is exactly the same, except you build a proof hunter over ZFC, right? That lists out possible proofs and checks to see if they're valid proofs according to the set theory axioms. And then if you could use that to always decide whether or not a Turing machine halted or didn't halt, you'd have a solution to the halting problem. This may make it a bit more surprising that if we restrict our Turing machines to not be able to write over the input, they actually are restricted to recognizing regular languages. The tape of a Turing machine consists of two parts, right? The part that we write our initial input word to, and then we have an infinite amount of tape afterwards. And this part of the tape we are welcome to use for both reading and writing. We're welcome to use that for whatever computations we want. But these read-only input Turing machines are going to be restricted if they attempt to write over one of these characters here. The operation will simply fail. And I guess we could put in a thing that tells the Turing machine that that operation failed, but it can also detect if it tries to write to a particular position and that operation failed by just checking before it moves on. Now, of course, every regular language can be recognized by a Turing machine that doesn't write over its input. And the way to see that is that, well, a deterministic finite state automaton is actually a very limited sort of Turing machine. It starts at the beginning, it always moves to the right every turn. It does not write to any positions. It just reads the characters at those positions and updates the internal state of the Turing machine. And once it gets to the end, well, I guess it has to go one more to see that it got to the end and read a blank character there. But once it gets to the end, you simply, based on the state of the Turing machine, either accept or reject. This is, except for the bit at the end, exactly the construction of a deterministic finite state automaton. But somehow the fact that our read-only input Turing machines, these are an extension of the deterministic finite state automata, somehow the fact that they can move back and forth while reading the input, or move out to this section here and write some information and process that information in fairly complicated ways. Somehow adding those possibilities does not make these machines recognize any new languages in terms of the inputs that they accept. One of the ways that I like to see this is that fundamental to a Turing machine's operation is marking a position in the input and then going out and doing some calculations and then coming back, being able to recognize where we were at that position to continue reading the input, grab some more data, go out to the processing part of the tape, and then go back to the input part of the tape. Because, of course, just having that functionality, just having the ability to mark positions on the tape where we were, and then go out and then do some stuff, and then come back, and being able to recognize where we were when we left, that's enough to do whatever a Turing machine can do. All you have to do is go through the input character by character, mark where you are, go out, drop off that data, write this character to the read-write part of the tape, and then come back, grab the next character, drop it off, go back, grab the next character, drop it off, and by being able to mark where we were, we're able to do this process and grab the entire input and bring it out to the read-write part of the tape. And then we just do what we would do as a Turing machine, processing this information, being able to both read and write to it. Of course, Turing machines have the ability to do more than just mark a particular position within the input. They can just completely write over the input and scrap that information. Although this is considered to be bad programming practice, because what if you write over some information that you need access to later on? And I hope in this video to give you a little bit of a sense of how to recognize when certain situations are modeled by deterministic finite state automata, when the thing that we're looking at is really just regular languages. The way to do this is imagine that we have a deterministic finite state automaton that's reading through these characters one by one, and this is not allowed to go back because it is a DFA. It reads through the characters one by one, and the question is, after having read, let's say, we've read these three characters here and we haven't read these characters here. What information do we need to capture about these characters on the tape in order to be able to continue our processing? When it comes time to process these characters, what information do we need to retain about these characters in order for that processing to happen? I like to imagine this part of the past as being an unknowed void and no longer accessible. Our deterministic finite state automaton, unlike a Turing machine, can't go back and gather more data. So what data did we need to capture in order to be able to continue our computation? And of course, when we're asking the question, what data do we need, the right way to think about that question is in terms of the Myhill-Nerode Theorem, which tells us exactly what information we need in order to be able to decide whether a particular continuation of this beginning, a particular future, winds up putting us in the language or not. Another way to think about this is that the deterministic finite state automaton is carrying information through time. And the question is, what information do we need to be carrying at any one particular point? With the idea that we can only carry a finite, bounded amount of information at any one time. So I'll give you a moment if you want to think about this problem. It's tons of fun, although it is a little bit tricky until you figure out the right way of thinking about things. So be ready to take a bit of time to try to solve this problem if you want to solve it on your own, and don't feel bad if you can't solve it on your own. Why is it the case that if we restrict our Turing machines to only be able to read and not write over the input, do they wind up accepting a regular language? In other words, how do you construct a finite state automaton? Given a particular Turing machine, how do you construct a particular finite state automaton that accepts a word if and only if the original input, read-only input Turing machine accepts that word, right? The fact somehow you have to deal with the fact that your finite state automaton can only move to the right, and this read-only input Turing machine can also move to the left, but it can't write to these positions. Imagine that the automaton is, let's say, here. It has read these 4 characters, it's in some state, and it's about to read these characters, but it hasn't read them yet. So somehow, everything that we need to know about the behavior of our particular Turing machine on this part of the tape needs to be encapsulated into some data structure of which there are only finitely many possibilities. The first thing that data structure is going to need to capture is what happens when we start our Turing machine, right? Our Turing machine starts off pointing at this first position on the tape in the starting state, and it's going to move around and do something on this part of the tape here. And in terms of this point here, in terms of the behavior that we want to capture for this part of the tape, there's only 4 possibilities. One is that before it gets to this point here, it stops and accepts. Another is that it stops and rejects. It may be the case that we have a Turing machine that just determines if the first character of our word is an A or not. And in that case, it doesn't need to go this far out. It can just look at the first character and it's done once it's read that first character. Another possibility is that the Turing machine gets stuck in an infinite loop somewhere in this first part of the tape. And then finally, there's the possibility that the Turing machine head actually makes it out of this first part of the tape. And when it does so, the only thing that we care about is what state it actually leaves this first part of the tape in. That's the only information that we need to capture in terms of, we don't need to know what states it was in on this part of the tape. We only need to know what state it left this part of the tape in. And so that's a finite amount of information. If this input word is really, really long, right, we could imagine lots and lots of characters here. We can't store all of those characters in memory. Both the finite state automaton and the Turing machine only have a finite number of states that they can be in. And eventually this word here is going to be too long to store the entire word within memory. The only important information that we need here is what state the Turing machine head leaves this initial section of the word in. And if the Turing machine head doesn't actually go back into this section of the word, that's all the information that we need to know, is what happens when we start the Turing machine. Does it accept? Does it reject? Does it go into an infinite loop? Or does it leave this section in a particular state? But unfortunately, unlike the finite state automaton that can never go back, the Turing machine head can go back. It can go back into this section of the input word. Lucky for us, it can't modify this section of the word, so it can't get up to too much trouble. If we send the Turing machine head out past this line backwards, what information do we need to have about this part of the tape? What information does our finite state automaton need to store in order for us to be able to figure out what happens when the Turing machine head gets sent back into this section? Well, we simply need to know. If we send the Turing machine head back into this section, does the Turing machine wind up halting and accepting, halting and rejecting, or going into an infinite loop, or does it eventually come back out? And if so, what state does it wind up coming back out in? And the answer to that question, whether it accepts, rejects, goes into an infinite loop, or comes back out, the answer to that question is going to depend on what state we send the Turing machine into this portion of the tape in. So what we're going to need to do is create this giant table. It's going to need to keep track of when we start the Turing machine, what happens? Does it exit the first part of the tape in a particular state, or does it accept, or does it reject, or does it go into an infinite loop? And then for each state of the Turing machine, we need to keep track of if we send the read-write head into this section of the tape here, what's going to happen to it? Is it going to accept? Is it going to reject? Is it going to go into an infinite loop? Or is it going to come back out in a particular state? So we have a table of each of those for every state of the Turing machine. And all in all, this giant data structure captures all of the information we could possibly need to know in terms of figuring out what our Turing machine is going to do. All of the information that we need about this part of the tape is captured in that giant data structure. And while this data structure might look large, it's important to realize that it's bounded. There are a bounded number of possible configurations for this data structure. So we can store this information in a bounded amount of memory, whereas storing all of the word up to this point requires an unbounded amount of memory, because who knows how long the starting bit of the word could be. Looking at this particular diagram here doesn't really capture that. There's only 4 bits of data here for this entire bit of the string. But it's important to realize that we could be looking at a really, really long string here. At which point it does make sense to store all of the information that we need about this part of the tape in this more complicated table data structure, as opposed to just storing all of the characters. So these tables make up the states of our finite state automaton. And we could, if we wanted to, eliminate some of them. We don't really care about any of the other information on the table. If the Turing machine starts here and winds up accepting or rejecting before it crosses this line. So all of the tables that start with either accept or reject, or even go into an infinite loop as their first entry, all wind up being equivalent to each other. We don't need to keep track of any more information. So if you wanted to, you could go through and use the Myhill-Nerode Theorem to minimize this automaton, to really get rid of all of the information that we don't really need to be keeping track of. But I think that's going to be more trouble than it's worth. So if these tables are the states of our finite state automaton, how do we determine what the transition function is? Well, suppose that we have a table capturing all of the information for this part of the tape here. We know what happens when we start the tape. We know what happens when we send the read-write head into this section of the tape, how it comes back out, or if it doesn't come back out. We have all of that information. How can we update that information for a new threshold? If we start the Turing machine at the start of the tape in the start state and let it run, of course, if the Turing machine eventually accepts or rejects in this part of the tape, it's going to accept or reject or go into an infinite loop in this part of the tape. Right? We don't actually need this character. The head never actually reaches it. That information is the same. On the other hand, if the read-write head actually does exit this portion of the tape, actually does cross this threshold in a particular state, well, then we need to figure out what happens when we read a B in that particular state. If we move to the right and enter a particular state, well, that answers our question really easily. We know what happens when we start the Turing machine. We know that it crosses this threshold in this particular state. On the other hand, our Turing machine might stay where it is and just update its state, in which case we have to ask, well, okay, what happens if we read a B and we're in that state? And of course, if it moves to the right, well, then we know what to do. If it stays put, then we keep going, and either we're going to get stuck in an infinite loop just staying here, or eventually we're going to move left or right. If we move right, we know what to do. If we move left, on the other hand, well, we have the data to figure out what to do with that. If we are in a particular state and we read a B and we move left going into a particular state, then we know what happens. We have that information in our table. We can look up whether this Turing machine is going to accept, reject, go into an infinite loop, or it's going to cross this threshold in a particular state. In which case we do our analysis again. If we read a B and we're in that particular state, do we move left, do we move right, or do we stay put? And we can just keep doing this analysis because there's only finitely many possible states. It's actually fairly straightforward to do this. We can figure out, does this Turing machine go into an infinite loop where it gets maybe stuck at this B, or maybe it keeps getting bounced back into this section, or does it eventually cross this new threshold into this position here? So that's how we update the first entry of our table. What happens when we start the machine in terms of this threshold here? Does it accept, reject, or get caught in an infinite loop before it reaches this threshold, or does it eventually first cross this threshold in a particular state? The process of updating all of the other entries into the table is essentially the same. If we move past this threshold in a particular state, well, then we have to ask ourselves the question, what happens when we read a character B and we're in a particular state? Well, either we move right, in which case, well, we know how to enter that as a table entry for here, or we move, well, or we stay put, in which case, well, we check what happens when we read a B and we're in that new state, or we move left, in which case we look that information up on the table. So the actual process of updating the table is kind of tricky, but it is doable. We have all of the information in the table for this threshold that we need in order to work out what the information is for the table for this threshold. And that's exactly what we're looking for in a transition function. So now we can construct our transition diagram for our finite state automaton. Each state is going to represent a possible configuration of these tables, and the way that we update the state is this very complicated thing that we have to figure out. We also know what the start state is, and honestly, I'm not sure if it makes sense to view the start state as happening before we read the first character or after we read the first character, because I'm not sure if there's any insight to be gained. Very often when you're doing these sorts of recursive, inductive constructions, there's something valuable to be gained by looking at the 0 case as your base case as opposed to the 1 case as your base case. I'm not entirely sure if that's true for this problem. I'd need to think about it some more. But either way, we can work out a start state for our automaton. Here's the final question. What are the final states? What are the accept states for our automaton? When we get to the end of our input word, and we have this giant table of information about, first of all, when we start the machine, when does it first cross this threshold, and then we also know about what happens if we send the read-write head back past this threshold. We have all of that information, and now we have to somehow weave all of that information together in order to decide whether or not we should accept or reject this word. We have all of the information that we could possibly want. There isn't any other information about this input word that this Turing machine here could care about in any way. But how do we decide whether this table means we should accept or reject? Well, we have to solve the halting problem for a slightly modified Turing machine. We have to solve the halting problem for a Turing machine that starts off here. It has the same transition function as our original Turing machine. It's just that the start state is whatever state we first cross this threshold in. And then we have a special lookup table that says if the read-write head is here and you tell it to go left, either that automatically accepts, automatically rejects, or automatically goes into an infinite loop, or comes back out in a particular state, depending on which state you sent it in at, as opposed to a normal Turing machine where, I mean, if I have a normal Turing machine and I tell it to move left past the start of the tape, I think the default, I really like the default of just saying, oh, nothing happens, it doesn't move. It updates its state, but it doesn't move to the left. But this modified Turing machine, the state changes somehow when you tell it to move to the left from the start state, depending on the lookup table. And this modified Turing machine, starting here, doesn't have any input to it. It's just a blank tape. It's just as if we started our Turing machine here. So the behavior of this modified Turing machine isn't going to depend on the input because it doesn't have any input. It's going to depend on this lookup table, but we consider that to be part of the modified Turing machine. So we just need to figure out, does this modified Turing machine, starting with a blank tape, wind up accepting, rejecting, or not halting? And again, many halting problems are solvable. There's lots of Turing machines, lots of computer programs that you can look at and you can say, yeah, that Turing machine definitely does halt and accept. or that Turing machine definitely goes into an infinite loop, or that Turing machine definitely, it doesn't loop, but it still never halts. We just don't have an algorithm for solving all Turing machines. Our original Turing machine could have been one that ignores the input completely, and then on this part of the tape does some halting problem nonsense, like print out its own code and try to prove that it itself halts or doesn't halt and does the opposite. It could do some, some nonsense like that. In which case, the modified Turing machine that we construct would just start in the start state and on this blank tape print out its own code and try to prove whether or not it halts or doesn't halt and try to do the opposite. But one of the things that mathematicians like to say is, well, I don't need to know the answer. All I need to know is that this modified Turing machine either halts and accepts, halts and rejects, or doesn't halt at all. Because no matter what the answers are, when we turn the appropriate states into accept states and all of the other ones into not accept states, it's going to be the case that we have a deterministic finite state automaton recognizing exactly the same language as the original Turing machine. In other words, we know that our original read-only input Turing machine is equivalent to some finite state automaton, but figuring out which one requires solving a halting problem. And so we don't have an algorithm to determine which finite state automaton it's equivalent to in every single case. We don't have a universal algorithm for doing this conversion. So I hope you enjoyed that tangent about Turing machines. I was absolutely flabbergasted when I saw this result that Turing machines that can only read the input wind up being equivalent to finite state automata. I originally thought, oh, I can't be reading that correctly. It has to be the case that these are read-only Turing machines that can't write to this part of the tape. But no, these Turing machines can read and write to this part of the tape. They just can't write over the beginning part of the tape. And somehow that limitation is enough to keep these Turing machines mostly in check. There's still undecidability going on, but we're also looking at regular languages. So I promise that really is it for the Turing machines diversion in this video series. Please let me know if you have any questions, if there's something that I haven't explained fully enough down below in the comments, and I hope to see you in a future video.